This will be a very quick presentation. We just want to introduce these ideas. I start by explaining the very basics, and we'll sort of layer on the knowledge as we go through the presentation. Models and simulations, I'll explain what they are, but they're essentially tools that are underutilized where they are most needed, and they are most needed in cities that are challenged with very rapid growth. And these are essentially tools that can help us answer what if questions. So in this very brief talk, I would like us to develop a fundamental understanding of transport modeling and traffic simulation. They're two different things, and I'll get into that. How they can be used to enhance the project development workflow, the different applications and data requirements. These are tools that you need to feed with quality and up-to-date data. So we'll look at that. And if it's something you're interested in learning and developing capacity around, I can also point you towards relevant resources for you to start learning. First things first, what is modeling? I'm sure you've encountered the term many times. You may have worked with different business models. You have architectural models. You have also financial models. You might have your own personal finance model that you can use to track how much money you have, and you can project into the future how much money you might have by the end of the year by knowing how much you spend. And with certain inputs, you can derive certain outputs, and it's very similar principles, but applied to the transport sector. And so essentially a model is a representation of an object or a system. It's a simplified version of something. And again, you've seen these before. An architect will work with physical models, a scaled down version of something. A transport planner works with schematic maps that are a representation of reality, but they're not to scale. A business model is a verbal model, and a transport model is a mathematical model. That sounds scary to some of us, but fortunately we have tools that do all the math and we get to do the planning. So a transport model is a practice and process that uses mathematical models in software tools to virtually test, appraise, and visualize complex concepts. Again, in the last session and in yesterday's sessions, we talked a lot about you having to work in a context of growth, very rapid growth. And your job is to find ways to better balance the supply and demand of transport systems in the present, but also in the future. You're all thinking about how your cities will perform in the next 5 years, but also 2030, 2050. And that's quite challenging because there's so many variables at play, and there are tools that can help you with that. And time again, we see in rapidly developing cities, we see big infrastructures planned and financed without a good forecast of future demand. And that can often result in infrastructure projects that are delivered over time and over budget. There are some very useful tools that you can avail of to help you overcome these challenges. On one side of the spectrum, we have transport models or transport planning. On the other side, we have traffic simulations for traffic engineering. So planners will use the models, engineers the simulations, and we can look at the spectrum using this kind of illustration where on one end, the model for planners is called a macroscopic model. You could have a model for all of ASEAN or all movements in the Philippines, including your road-based traffic, but your rail as well as your air traffic, your boats. You could have a model at that national level, or you could have a metropolitan level model, say for Metro Manila, or for your city, or for part of your inner city. But then we get quite detailed, and the more detailed we get, the more we move towards the world of traffic engineering. And the difference there is one is link, node, and zone based. This is like a 2D map that you're probably familiar with, made up of lines. And you can also have different zones. This could be an administrative area, or a node would be an intersection. And all your data is stored around links, nodes, and zones. And I'll make that a little more clear in the next few slides. While on the other end, you have simulations, which is agent-based. Basically, you have autonomous agents moving through a network like this. So the car is an agent, the person walking is an agent. In theory, you could have a simulation of your city, but it would require a lot more computing power, and the margin of error would increase as you go up in scale. So we rely on models. And models are great. I am a big advocate, but of course, the real world is far too complex for these models based off of algorithms to effectively and very realistically model. And so they're only approximations. Your job, if you're a modeler or someone working in simulation, is to get it as close as possible to reality. But that in itself can be very challenging, especially in the Filipino context, I imagine. You have so many different vehicle types, and the behavior of these vehicles is really quite complex. Jeepneys don't necessarily park at consistent locations. So modeling gets quite difficult in this kind of context. But you also have to consider the risk of not modeling. If you create a project without modeling, maybe your outcomes will be even further off from what is needed. And when you build a model, there's a workflow, and this applies to simulations too. Before you even begin, you will need an idea for a project, a vision, and a desired outcome. And your desired outcome could be, say, to reduce congestion or improve traffic flow. And then step one is to build what we call a base model, a model or a simulation of what's happening today in real time. So the current situation. And to do that, you collect data. It could, for instance, be traffic counts. You then build your model, and then you calibrate your model to make sure it closely resembles what's happening in reality. And that could be a whole session in itself on how you can calibrate a model. But for example, you could compare your model to the collected data and or to, say, CCTV footage of the given area you are modeling or simulating. And then once you have your base model, you can create scenarios. So your vision could be delivered in many different ways. Say this is our project location. We have a big roundabout with a green island in the middle. Say you want to improve traffic flow. You need different kinds of data to build, say, your base model. You need information on the road network. So you could get that from a CAD file that you may have at the city level, or you could extrapolate it from a GIS map you may work with. You need traffic counts, information on vehicle compositions, so the different types of vehicles, driving behavior. People drive differently in different parts of the world. If you have traffic lights, you need to know your traffic signal cycles. And if you want to make it a pretty simulation, in this case, you would need maybe some 3D objects, some buildings, some trees. So that can be our first scenario. And maybe our engineering and design team comes up with another idea. What if we have this pedestrian overpass goes over the roadway, and we want to test and see how that performs? Or we have another scenario where we have a much more expensive looking project where we create essentially an urban garden and have the traffic in the intersection go below that piece of infrastructure. And this is a bit of an elaborated example. You could do something much more simple. Just compare different traffic signal configurations, for example. But basically, you build your scenarios, you can test them, evaluate them, and then compare the different results and see how they perform. Then it's up to you to choose whichever best meets your desired outcome or key performance indicators. And once you've done that and you've selected your scenario, the workflow continues and you can go to a detailed design stage. And say this is the model we go with, then you get useful numerical outputs, but you also get nice visualizations. And again, we're doing this at a very high level, so we'll only be showing you some of the nice visual outputs. And this is quite useful for you if you work in a technical capacity. If you have a good idea for a project and you want to share it with your mayor, instead of just handing him a 200-page report, you can give him a nice video which can be quite convincing. And I'd like to just deep dive first into macroscopic modeling for planning, and then we'll go into microscopic for traffic engineering. and your macroscopic model, your large-scale model that is used to answer what-if questions. What if I build a new road here? What if I make a change to my public transport? Say you change the route or you change the schedule. What if I create a new development? If you introduce a new stadium or a new mall, what impact will that have on the wider transport network? What if there's a demographic change? You have an aging population or you have just a very fast growing population, which is the case in many of the cities. What if mobility prices change? If fuel costs go up, that will impact how people move. Also, what if you introduce new regulations? These questions could be answered in a model-based environment, but obviously you need a lot of data to feed the model. As for solutions, there's a lot of different tools out there that you can use. They all have their relative strengths and weaknesses, but what you choose to use, you will probably stick to because there is quite a steep learning curve when it comes to using these tools. So it's worthwhile really exploring what's out there and seeing what best meets your needs. And the way the tool works, there's really 4 different pillars. The first is it acts as a data hub, as a tool where you can centralize all your different supply and demand, your spatial data, such as your transport network. You can have all your roads, primary, secondary, tertiary roads. You can import those from, say, OpenStreetMaps if that's what you're using. You can also import your public transport network. You can also bring in land use and socioeconomic data, so your administrative boundaries, population, economic data. So all of this can be brought in to your model, which is pretty much what you would do with a GIS tool. And at this level, it's essentially a GIS tool. And it could look something like this. So here we have our zones. So we could have Metro Manila and then have all the different cities represented as zones, for example. We've also overlaid our private transport network and our public transport network. And we can click on any given road and get information, the attributes of this road. So how long it is, the capacity of the road, how many vehicles can move through it in, say, an hour, the driving speed, and you have this for each and every road, which we call a link. And that becomes very useful when we get to the traffic analysis stage. You can also get data on your zone. So here we're clicking on zone number 10, and we can see related information. So we could have socioeconomic information about the zone or information on where people are going to and from. A lot of these tools are based off of origin destination data, and you get that information in different ways. It could be from a household survey, but you start to understand how people move between zones. And in this particular example, there's 2 universities, one here and one here, and you can see a lot of movement, high volumes of movement. The volume is represented by the thickness, and you can see how people are moving through space. This is not assigned to the road network, so it's still not very useful, but we do get an idea of how people are going to and from different locations. Once we've got our data hub ready, and if your city has a data hub that's up to date and well maintained, it's an extremely valuable tool to have, which you can then use to quickly test and appraise different project interventions and do all kinds of traffic analysis. So say we have our model, we have it all set up, it's our data hub, and we have our origin and destination data. And basically what we do is we run an assignment, we click play, and we can see how people move through our network. This case here, we have public transport in blue, private transport in orange, and we can see the volume. And you could also visualize it in a way where you can see where you're likely to have congestion. And that can help you identify underperforming locations, measure delays, and determine just the general level of service of your transport system. And that can give you a really good idea of your network capacity and network performance, which is insightful. But when it becomes really useful is when you use it to develop forecasts. So you need to have a good baseline and base model to then develop forecasts. So again, say this is your city. You have some bottlenecks as you approach the city center there, and you would like to understand what impact having a new road would have on decongesting the city center, for example. So anyway, in the model, you have your data hub, and very quickly you can do analysis like this. So say we want to test this hypothetical road. We run a new assignment, and we can see the volume that has shifted onto this road because we know origin, destination, and some people that start over here want to go over here, and now they don't have to go through the city center. And you can see if I go back and forth, how the volume moving through the city center has decreased. Quite useful to quickly test and appraise different types of interventions. And that's quite useful because if you can understand the extent to which you can potentially reduce congestion, you can do all kinds of economic appraisals. You can do some kind of cost benefit analysis on what's being proposed. And that can also help you develop your financial proposals. It can also help you inform your civil works. You can determine how many lanes you may need for this given road. You can quantify congestion reduction. And again, you can do all kinds of cost benefit analyses. Hopefully, you opt to use these tools for more sustainable urban mobility purposes around the different topics we've been presenting. And one way these tools can be used is for public transport. You could test the potential impact of a new bus corridor, for example, and you could identify the most optimal location for your corridor based on your origin data analysis and find the best suited corridor for, say, a high capacity bus corridor. And you could also use it to develop your schedules and understand how your vehicle performs. So here you can see at 6:45 in the morning, going towards 7 a.m. between Central Station and Market Square, there's a lot of passengers on the bus to a point where the level of service is quite poor for the passengers. And this could maybe indicate that an additional bus operating between this time frame would be beneficial and would improve the passenger user experience, which is quite a nice thing to be able to determine early on when you explore these kinds of projects. You can do all kinds of visualizations to understand accessibility to and from city centers or to and from different stations. So there's a lot of other kinds of analysis and visualizations you can do using these kinds of tools. Again, can help you enhance your implementation. You can determine how many BRT vehicles you may need to run your service. You can understand your fuel requirements based off of that. You can also optimize your service operations, which will maximize your fare box revenue. Over to the other end of the spectrum, looking at traffic engineering. So now we're looking at microscopic simulation. It's a whole different profession that would use these tools. This one is much more visual, and you can use it for designing your cycle lanes, perhaps, for public transport operations, and I'll give some examples, and also for traffic signal control. And these tools have slightly different applications. Again, much more detailed, but you can do capacity analysis, but at a very localized and detailed or granular level. I'll give an example of traffic signal optimization and public transport, but you could also do emissions modeling, and you get these nice visual outputs. Obviously, behavior differs from city to city, country to country, culture to culture. This particular tool is developed in Germany. People drive very differently in Germany. They're very obedient of traffic lanes. However, in much of the world, probably the majority of the world, we don't abide traffic lanes quite as much. So if you want to build a simulation that reflects reality, the simulation needs to be able to simulate non-lane based traffic. So here you can see the motorbikes, if they see a gap, they will take that gap and they will move into that gap. And there's some bunching beyond the intersection, which is closer to what we would maybe see in some Filipino cities. This is an Indian city. And again, you can see the vehicle composition, the types of vehicles you see should and can reflect the reality on the ground. The simulation is based off what we call the Wiedemann car following model. It's an algorithm. Basically, vehicles don't drive at a constant speed from each other. They get closer and further away. And that differs, again, from country to country and culture to culture. Some countries drive much more aggressively, some less aggressively. And your simulation will need to be tweaked to best reflect the local reality, which is complicated exercise in itself and could require some extensive research if you want to do it very accurately. Here, I just have a nice story of a project. Does anyone know where this is? This is the city of London. It's a very old photograph, as you've probably guessed. It's of a time when London had a much, much smaller population, much, much fewer vehicles, and it's arguably one of the hearts of the city center. It's called Trafalgar Square, yes. And it used to be one big multi-lane roundabout, 2 or 3 lanes here, 4 lanes over here. But as the city developed, it just became an island of pollution. This is it today, 100 years on, in a much bigger city, much more populated, much more motorized. And what can we observe here from this image? There's one key difference, and it relates to the previous module. It's no longer a roundabout. Yes, so they pedestrianized an entire section of what used to be a roundabout. Now it just forms one big public space. So how can they do that? A city that has only grown since this was initially built has probably 10 times the population, 10 times the vehicles. How can you reduce capacity and still keep traffic flowing? And you can see here, this became pedestrianized. They reduced the amount of lanes, and they created a small roundabout in front here at a very critical location in London. And this was a UNESCO project. This was deemed a valuable public space in London, and they received funds to improve this as a public space and improve the air quality. And how did they do this? Well, they developed a simulation, but essentially what they did is they tested a queue relocation strategy. So using actuated traffic signals, so on-demand signals, essentially traffic lights that know how many vehicles are waiting at a arm of the roundabout, they redesigned how the traffic signals function. So basically there's traffic lights here, 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 and also upstream. And if this traffic light detects a 60% threshold, if it feels like it's getting congested, and it knows this from sensors, loops in the street, it will tell the traffic light upstream to hold the traffic back. And so this can only get congested to a certain point because the traffic signals will hold traffic back. And yes, you will build up some traffic further upstream, so at an intersection like that one. But as long as the roundabout doesn't completely congest, you can maintain a certain amount of flow in the city. And the only way this project was ever approved is because they could test it and show that it could work. And this was done using a simulation solution like this one. So quite a nice idea of how you can use these tools to better manage traffic to improve the non-motorized transport environment. So that's just one example. You can use it for many different purposes, for understanding travel times, travel volumes, vehicle emissions. And then going even at a more detailed scale, we also have pedestrian engineering. And this is, again, similar concepts, but obviously people move very differently to vehicles. And this is not based off the car following model, but off what we call the social force model. And similarly, that needs to be calibrated to the local culture. So in a Northern European city, people keep their distance when they are existing. Whereas in the Philippines, I feel people are fine being close together. And so when you simulate a pedestrian simulation, you can calibrate it to the local setting. And you can use this to determine the level of service. A level of service F, as you can see here, is very crowded, so probably not a very comfortable way to experience an infrastructure. Level of service A, you have lots of space, free circulation. And if you can strike for level of service C, D, it gets a bit crowded, but that's generally something good to aim for. And say you're building a new transport hub, you could, before building anything, understand roughly how people move through this space and see where you may have a poor level of service. If you haven't designed it yet, you could work with your architecture team to design in a way where the level of service is aligned with your train schedules, so you know what and how your station may perform, say, in the peak hour. So lots of different applications. It's quite useful also for multimodal engineering. where vehicles meet pedestrians, complex intersections could benefit from using the vehicle plus pedestrian simulations. If you want to plan, again, your BRT corridor, or if you have big events and you want to make sure people can leave, say, a stadium in a certain amount of time if there's ever an emergency, similarly with a building evacuation. And I just want to wrap this up with a very quick example of how different tools could be used together to help you with the development of, say, a project. And I've used the BRT example. You would start with using these tools for the planning purposes. You would develop your data hub. You could use that to help determine the optimum corridor. You could do your scheduling. You could determine your vehicle fleet size requirements. You could also understand, if you have a dedicated busway, what impact that would have on the traffic. And then you could go import parts of your corridor into a simulated environment. This is an example from Abu Dhabi. This has not been built. Here you can move 10,000 people per hour per direction by removing a lane of traffic, versus here where we have 3 lanes of traffic versus 2 here. You only move 7,000 people per hour per direction, which we talked about this morning as well, the people per hour per direction, the PPHPD. And you would use this tool to design your lanes, the interaction of the buses at intersections with vehicles, and also your stations. And I should have some examples of stations. This is a multimodal station in Colombia, where they have the Transmilenio, a very famous BRT. And you can see how this tool may have been used for the design of the station. You have passing lanes so buses don't bunch up, which is good. You need to have platforms long enough to cater for the demand. You could also use a tool like this to see how your BRT could integrate with your feeder services, which could be jeepney based, for example, and also understand the pedestrian or the passenger user experience by determining their level of service. And even simple things like, how many turnstiles do you need for people to move comfortably through your stations? You could sort of see how queues build, which is quite nice. At the most detailed scale, you could even use a tool to determine the added benefit of, say, having a bus with 2 doors versus 3 doors. If you have 3 doors, you can board and alight more people faster versus 2 doors, obviously. And if your whole network is composed of 3-door buses, but 3-door buses cost more, but your service operates more efficiently, you could do some kind of cost-benefit analysis. So again, some of the solution providers, they provide integrated tools where you can really move through this entire workflow in quite a seamless fashion, from macroscopic to microscopic, which is quite neat. And that's really good for planning, engineering, designing, economic appraisal, and accessing finance. If it's something you wish to learn more of, there's no better time to start than the present. If you start today, you can avail of much better tools than existed, say, 10 years ago. We have much more data. There's new methods to access data. Our computers are better. Costs are lower than ever for a lot of sophisticated hardware and software. And we have new automated methods. If you wish to get started, I'm happy to guide you towards some useful resources. There are different demos of different software packages online. So I can only recommend trying out the different tools, see what works best for your needs. And if you find the tool you like, there's lots of online communities of practice that you can join and learn and ask questions. There's some very passionate people in these worlds of modeling and simulation. And yeah, start with a very small project. And if it's really something of interest, you can even check out our website. We have a more extensive talk on what these solutions are and a basic training exercise that shows you how to download a software package and how to build a very simple simulation. I hope it was interesting, and even if you never pick up one of these tools, I think it's useful for you to know that they exist. So thanks very much. SMMR is an ASEAN-German cooperation project implemented by GFA Consulting Group and partners on behalf of GIZ. For more information on the summer project, do consider checking out www.summer.asia. We look forward to seeing you there.